We have one last example of linear motion that's not along the x-axis or y-axis in terms of a traditional Cartesian coordinate system. We call this linear motion on a slope or incline. So a common example would be a nice straight slide at the park, and a child can slide down the slide. Now we are going to make the assumption at the moment that there's no friction. That's not the best assumption, but we will start accounting for friction when we get to forces in section 2. So this slide, for example, or it could be a hill that we're driving a car down. Probably the best example would be a nice straight sledding hill so that there's snow, so this idea of no friction would make more sense. So this here is our slope or incline. When we talk about the acceleration along a slope or incline, we are talking about the acceleration portion that points down the incline. You could call it a sub incline if you want, a sub slope. We just need to recognize that the acceleration points down the incline, meaning if we were sitting at the top of the snowy hill on our sled and we just start going, we're going to speed up. We're going to go faster and faster and faster and faster as we slide down the hill. So that's what we mean by A of the slope pointing down the incline. Now, ultimately, it's because of the acceleration of gravity that we're accelerating in the first place. But we are not able to accelerate at 9.8 meters per second squared because the ground is in the way. The ground's not making us speed up or slow down directly, but because the ground is not allowing us to fall straight down, it does affect the acceleration that we experience. Now, the derivation of A on a slope comes from understanding vectors, which we're going to talk about in the next chapter. For now, we can use the equation that the acceleration of an object on a slope is plus or minus g sine theta. G meaning our magnitude, our just the value, 9.8 meters per second squared of the acceleration due to gravity. Plus or minus because we need to impose and talk about a specific coordinate system when we solve a problem. If we choose a coordinate system, essentially what we're doing is we're making the line of the slope our x-axis. If we call down the incline the positive x direction, then we would use the positive value for the acceleration on the slope. So in this example of coordinate system, we would choose plus g sine theta. But it's totally valid to choose up the slope. Let me draw a new slope. And by the way, theta in this equation is the incline of the slope measured from the horizontal. In this second slope, A on the slope still points down, but suppose we were solving a problem where the object was moving up the slope and we wanted to call that direction the positive x direction. So we want to make the velocity positive. Then if we choose this specific coordinate system, then we would need to say that the acceleration of the object is negative g sine theta, meaning this object's going to slow down, and as it slows down, it will eventually reach a maximum height along the incline, slow down, and stop. So Let's do a couple of examples to go along with this. All right, I've pulled in a question here. It's a silly little question. We have Santa on top of the roof, loses his footing, so he slips and falls, and he slides down a frictionless snowy roof that is tilted at an angle of 20 degrees. Now, whether we could totally draw the roof on either side. When they say the roof is tilted at 20 degrees, that we're implying either side. It does not matter if we have Santa sliding down to the left or down to the right. We ultimately just need to choose which one we want to use and go with it. One is not any better than the other. So I'm going to just draw over here to the right. Let's say Santa is at the top up here, and he goes down to the right. So I'm just choosing this to be the direction. I know the acceleration points down the slope. That's always the case. This acceleration is the plus or minus g sine theta, which we will choose the correct sign, the plus or minus, based off of how we choose our coordinate system. The problem does tell us that Santa slides 10 meters to the edge, and we want to know how fast Santa's traveling as he leaves the roof. So he has a speed here. That's what we want to find. So in a situation like this, we do want to choose a coordinate system, and that coordinate system is going to be rotated such that the x-axis lines up with the slope. I'm going to go ahead and call down the incline positive, simply because in my drawing, that's the direction I have Santa moving. So it makes sense to make that positive. At least in my head it does. So this acceleration is constant as long as Santa is on the slope. G is 9.8, thetas are 20 degrees. So as long as Santa's moving along the slope, his acceleration is constant, meaning we can use kinematic equations. Again, I'm just writing them all out to talk about how to choose which one to use. I do want to, as we have in previous problems, write out the list of variables that show up in the kinematic equations. I'm going to go ahead and say my origin, I suppose I should have drawn it that way. My origin is where Santa is when he slips and falls. Finally, right as he's reaching the edge, the problem tells us he has traveled or slides 10 meters before reaching the edge. When he loses his footing and then slides down, we're implying he just fell over and then starts to slide. So there's no initial velocity to carry him down the roof. V final is what we're looking for. Our acceleration in this specific coordinate system I've chosen to use, the acceleration is pointing down the incline. That's my positive direction. So our acceleration will be positive 9.8 sine theta, or sine 20 specifically for this problem. They don't give us anything about time, nor do they ask for it. We do want to find this final speed as he is leaving the roof. Because there's no time given, I want to see if this third equation will work. There's no time in it, so if it works, then awesome. So V final squared, I'm going to go ahead, we know V initial is 0 in this case, so I'll leave that off. We have S final minus S initial, but that one also is 0 based off of our origin. So V final will be plus or minus the square root of 2a final position is 10. So V final. Now, just as a reminder, the plus or minus here, in physics, the plus or minus is always related to direction. And so in this coordinate system we're choosing, technically Santa will be moving in our positive direction. But we are asked for his speed. So we just want the positive value, the numerical value. So we'll take the square root of that. Oops, I have to turn my calculator on. I'm getting 8.1875, so forth. And I'm now actually seeing this question does ask us for how long. I didn't finish reading it, which we'll get that in just a minute. Sig figs, technically without the decimal places after these numbers, specifically 10 point meters and 20 point degrees, they technically have 1 sig fig. When it's a little ambiguous like this, I will totally accept 2 sig figs. So let's go ahead and just write V final in 2 sig figs. 8.2 meters per second. I would totally accept an answer of 8 meters per second because of the sig fig issue. So that's the answer to the first question. The second question, how long does it take him to slide to the edge of the roof? We want time now. We can either use the top equation or the middle equation. They both have time, and we do have enough information to solve either one. So whichever one you like better. Let's see, we don't have t squared in the top one, so it does look like it might be a little simpler to solve. V initial is 0. We have now calculated V final. We know A. I am going to use more sig figs when I plug in V final here. Again, just to minimize rounding error. And the acceleration, same value, the 9.8 sine 20. .4 seconds would be the time it takes for Santa to slide down to the bottom. So these kinematic equations, the big three, very useful as long as we know for sure we have linear motion with constant acceleration. So a slope, it's still constant acceleration. It's somewhere smaller than 9.8 because the ground is in the way. But this equation for A on the slope will work for any straight line motion along a slope right now when we're ignoring friction.